Hello there and welcome to the series of videos going through the content of A-Level Further Maths. Here we're looking at solving a cubic and a quartic that involve complex numbers so we can answer questions from exercise 1F. Now in case you missed the previous video to this, what's important to remember is that when you have a complex number being a root of a polynomial with all real coefficients, in addition to that complex number being a root, its complex conjugate will also be a root. The reason for that is that when you expand those two brackets with those complex numbers in, all of the i's pop out and you're only left with real coefficients. So it's really important that that is remembered throughout this video, and we'll see that appear time and again. Okay, let's start off with this question here then. We're told that given that minus 1 is a root of the equation x cubed minus x squared plus 3x plus k equals 0. Now what it means for minus 1 to be a root, in case you haven't studied it in A-Level Maths yet, is that when you plug x in as minus 1, the equation will work and it will equal 0 at the end. This here, we've got a cubic equation, a cubic polynomial here, and it equals 0. So when we plug in minus 1, we should get a 0 out at the end. Now one way we could try doing this is to substitute minus 1 in, and then we'll be told then what k needs to be to make that equal to 0. So substitute minus 1 in for all your positions of x, leave k alone, simplify each part, so minus 1 cubed is minus 1, take away minus 1 squared, that's 1, so take away 1, take away 3, and that plus is k to make a 0. So k needs to be 5 then. Okay, so k is 5, we know that, but the question here is find the other two roots of the equation. Now if we know that this is our polynomial here we need to work with, and if we know that minus 1 is a root, then we know that we can factorize this with an x plus 1. Now it's a minus 1 here. Why is it factorized with a plus 1? Well, it's because when you solve a quadratic or a cubic, when you've got a bracket of x minus 1, x plus 1, minus 1 is the solution when that polynomial equals 0. So minus the negative of this root goes inside the bracket here. So it's x minus 1 is going to be a factor of this polynomial here. You'll see a lot of this appear in A-Level Maths if you've got up to this topic yet. So what we should be able to do is find something that times by x plus 1 to give the answer of our polynomial that we're working with here. And that something will be something that can factorize as well, and that will give us all three of our solutions. Now this something's obviously going to look like a quadratic term here, a quadratic polynomial here, because the highest power in our original polynomial was a cubed, and we've got an x here, so the highest polynomial we need to have in here is an x squared. So using the box method, hopefully you've seen the box method in A-Level Maths, what we're doing here is a bit of algebraic division. We're doing x cubed minus x squared plus 3x plus 5 divided by x plus 1. Now how do we do algebraic division with the box method? Well, effectively what we want is for this part of the answer, our final answer, to appear on the top row, and all of what we've got as our big cubic polynomial will appear and simplify inside all of these boxes. So the first box, we need an x cubed, so that x squared times x will give us the x cubed. When we expand the boxes or expand the brackets, we're going to get a plus x squared down here, but we don't want plus x squared as our final answer, we want minus x squared as our final term for the x squared. So we're going to need to then take away two x squareds. So then above here is going to need to be minus 2x, because minus 2x times x gives us minus 2x squared. So we've got most of our answer. We've got x squared minus 2x, and when we expand the bracket with the 1, we're going to get minus 2x, We don't want minus 2x, we want positive 3x. We need to add 5 more x's on. So then we need an add 5 up here in the final part of our factorized form of this cubic polynomial. And it does add to make 5 at the end, so we know we've got this right. So we know now that we can factorize our cubic polynomial into x plus 1, x squared minus 2x plus 5. And for us to now find the roots of this equation, all that's left for us to now do is to find the roots of this equation here. So we've got minus 1 in there, that's the one we already know. And now we need to just factorize or solve this quadratic here. So we can use the completing the square method. And we get an answer here of 1 plus or minus 2i. So here we've got 3 solutions to this cubic polynomial. We have x equals minus 1, and x equals 1 plus 2i, and 1 minus 2i. Now it's no surprise here that we've got a cubic polynomial with 3 solutions here. In fact, that's always going to happen. If you've got a 3 here, you'll have 3 solutions. If you've got 4 here, you'll have 4 solutions. If you've got a pentic equation or a quintic equation, you'll have 5 solutions here in the complex numbers mode. That is effectively the fundamental theorem of algebra, that when you have a polynomial of degree n, you have n solutions. Some may be repeated, but in total you'll have n solutions. So yes, it's interesting, quite interesting. That's the fundamental theorem of algebra. Okay, so that's how we do that question there. So lots of steps. It required substituting in minus 1 to start with to work out what k needed to be. It needed algebraic division to work out what your second quadratic term is going to be, or second quadratic factorization is going to be, and then solving that quadratic equation to get the second and third roots. So lots of maths required there. Quite a tricky question. So in a cubic equation, either all 3 roots are real, or you'll have 1 real solution and 2 other complex conjugate pair solutions. Okay, so yeah. Okay. Now here we're going to increase the level of difficulty a little bit more. We're going to work with a quartic equation. Okay, so we're going to have 4 roots in total. So either in a quartic equation all 4 roots are real, or you may have 2 real roots and 1 pair of complex conjugate roots, or in fact you could also have 2 pairs of complex conjugate roots making 4 roots in total, but you will always have 4 roots basically. Okay, so here's another question. We've got 3 plus I as a root of the quartic equation of this big long thing here, 2x to the 4 minus 3x cubed minus 39x squared plus 120x minus 50 equals 0. And the question is, solve the equation completely. Well, first, if we know that 3 plus I is a root, we can get one of those roots without doing much work. We know that if 3 plus I is a root, then 3 minus I must also be a root. Because the complex roots always come in pairs in their conjugate pairs. And when we know this, we can now find a quadratic that will have these 2 as their roots, and we've seen how to do this in the previous video. It's called using the reverse completing the square method. If we know that x is equal to 3 plus or minus I, then we can substitute 3 onto the other side, square both sides, expand the brackets and add the 1 onto the other side. So we get x squared plus 6x plus 10 equals 0 as a quadratic that will be able to factorize this quartic equation here. So we know now that x squared minus 6x plus 10 is a factor. So let's now try and divide our original polynomial by x squared minus 6x plus 10. Now, what will have to be here to make it factorise? Well, it's going to be another quadratic term here, because you can see that when we expand, we're going to get an x to the 4 term at the highest degree. So now let's do a bit of algebraic division. Down the side we're going to have x squared minus 6x plus 10, and along the top will be our answer to whatever we'll factorise with x squared minus 6x plus 10 to make our original quartic equation here. Now remember, the original quartic equation components will fit inside the boxes here. So in the top left hand cell goes the highest power, so 2x to the 4. That means we need a 2x squared to be on the top there. That will make 2x to the power 4 in total. And remember, we're going to be multiplying the outsides, the dimensions of the boxes to get the inside parts. So let's go ahead and times to make the inside components, such as we've got here minus 12x cubed and plus 20x squared. Now what's next to appear is whatever we need to make this minus 3x cubed part. This should be a squared, there should be a cubed part here. So we've got minus 12x cubed to start with. We need to add on 9x cubed to make minus 3x cubed in total. So what needs to go on the outside here? It needs to be plus 9x to make 9x cubed. And what appears in the next brackets down here as we multiply, we got minus 54x squared and plus 90x. Now we need minus 39x squared, and we already have the combination of these two, so that would be it'd be a minus 24. No, minus 34, sorry, so we need to now take away another 5 x squareds, so take away 5x squareds, and how do we do this? We need a minus 5 up there. So now expand in the brackets to get plus 30x and minus 50. That good, we've got a minus 50 there, and we have got plus 120x's in total when we add up these two cells here. So great, so we've factorised our quartic equation into two quadratics, and our answer appears at the top here. So we've got our original quartic can be factorised into x squared minus 6x plus 10. We already knew that part, but the other parts that it will factorise into is 2x squared plus 9x minus 5. Now let's go ahead and solve that to get the last two roots of our quadratic equation, of our quartic equation. So we're going to be doing this either by trying to factorise, and if not, we'll have to go to completing the square or using the equation. In this case here, it does factorise nicely, so it's x equals a half and x equals minus 5. So those are our four roots of our quartic equation. For this big quartic equation here, we needed one root to just give us a little eye into the problem. We then got the second root here because it always comes in conjugate pairs, and then we did a bit of factorization, working out what the quadratic would be here, and then we did a bit of division to get the other quadratic, and then from there we got the other two roots. Okay, so we went through a lot there. Feel free to rewind the video and watch that play out again, or what you could do is you could have a go at this question here. We've got two questions on offer here. Here's the first one. I'll give you a second one once we've finished this one. So pause the video and have a go at this one to start with. Okay, so let's have a go at this question here then. So part A is show that f of 2 equals 0. So first of all, what we need to do is just substitute in 2 for the value of x, so the value of z. So that will give us 8 minus 24 plus 42 minus 26. And if we group together positives and negatives, we'll get 50, take away 50, which gives us 0, perfect. Part B, hence solve f of 0 completely. No, that's meant to be, sorry, it's meant to be f of x equals 0. So hence solve f of x equals 0 completely. Well, we know that 2 is a solution, so we have one root, which is equal to 2. And if we know that 2 is a root, then we also know that x minus 2 is going to be a factor when we factorize it. Now what else is going to be a factor here? Well, let's pull out our box method. We'll have x minus 2 down the bottom. We'll use x's, it doesn't matter whether it's x's or z's. We'll have x cubed in here to start with, and we'll have x squared on the top here to make x cubed there. Then we'll need minus 2x squared down here. Now we don't want minus 2x squared, we want minus 6x squared, so we need another 4x squared. So we'll need minus 4x to be here. So then that will give us a plus 8x down below here, but we want a plus 21x, and then we'll need to add on 13 more x's. So we'll need a plus 13 here, so that will give us a minus 26 at the end. Good, okay, perfect. So that's worked out very nicely. So please excuse the x's and the z's. It doesn't really matter what letter we use really. So we'll have x minus 2 bracket x squared minus 4x plus 13. All that's now left for us to do is now solve this because we want all of the roots. So we will complete the square, so it will be x minus 2 squared, and then that will give us 4 on the outside, so then all we need is a 9, so it would be plus 9 on the outside equals 0. Or we could say here that x minus 2 squared equals minus 9. And then when we square root both sides, we'll get x minus 2 equals plus or minus 3i, because it's a negative 9 being square rooted. So square root of 9 is 3, square root of the minus 1 is I. So here we're going to get x equals 2 plus or minus 3i. So here are our roots, 2, 2 plus 3i, and 2 minus 3i. Now you can also do a lot of this on your calculator. All you need to do really is go to the menu button, scroll down till you hit the polynomial mode. I think it might be option A, B, maybe C, I can't remember. Enter that you want a cubic, so option whatever it is to get the cubic up. Enter in the coefficients, so you want a 1, minus 6, plus 21, minus 26. You also need the I to appear up here. It's definitely in the setup mode, so you want to include complex solutions here. And all you then need to do is just press enter, and you get your first one is 2, great. Your second one is 2 plus 3i, and your third one is 2 minus 3i. So that's how you can check on your calculator you've done a question like this correctly. Alright then, so let's move on to this one here then, question 10. So pause the video and have a go at this one. Right, so let's have a go at this question 10 here then. So what it's looking for us to do is first of all factorize the quartic equation above here, and we already know that it factorizes with an x minus 9 term. So that means it's definitely got roots of plus and minus 3, and this will probably also help us find another quadratic that factorizes it so that we find all of the roots in total. So what do we need first of all? We need z squared minus 9 down the side, and our answer, which will appear here, which will be what it's factorized into, will appear at the top. All of the quartic equation should appear inside this box when it's all simplified. And the first term we need is the highest power to appear in the top left. And what do we need? We need a z squared on the top so that it times us by z squared to give z to the 4. And also down here, once we expand out all the boxes or the brackets effectively, we get minus 9z squared. Now we've got a z squared part here. We've now got to look for the z cubed part. We need minus 12z cubed. So what do we need? We need minus 12z. And also when we expand the brackets or expand the boxes with this, we're going to get 108z, which is kind of good because we've got 108z there. And then what do we need for the z squared part? Well, we need plus 31z in total. We've already got minus 9z, so we're going to need to add on 40 more z squared so that it simplifies to make 31z squared. So plus 40 down the bottom here. That's going to give us minus 360 down the bottom right here, which is exactly what we've got here. So you can see that all of these 6 boxes will simplify to make our quartic term above. Now what this means is that our quartic f of z is going to simplify or factorize into z squared minus 9 and then z squared minus 12z plus 40. So that's the factorized version of this quartic equation above here. And then for the last part, it asks for us to find all of the roots of f of z. Well, just from this z squared minus 9, I can quickly look at this and do a little complete difference of 2 squares, So the first roots are 3 and minus 3. And for the last bit here, I'm not too sure on this, so we'll complete the square. So it's going to be z minus 6 squared. That's going to give us a 36, so we need a plus 4 equaling 0. So then it will be z minus 6 squared equals minus 4. Square root both sides, and we'll get z minus 6 equals plus or minus 2i, because that's how we square root minus 4. So the 2 roots from this quadratic term are going to be 6 plus 2i and 6 minus 2i, from once we've added the 6 onto the other side. So z equals 6 plus or minus 2i. So there we are, that's our final answer then. 3 minus 3, 6 plus 2i, 6 minus 2i. When it's got a power of 4, it needs 4 roots. So that's how we know we've finished that question. Once again, you could do all of this on your calculator, making sure that you know which buttons to press. Hit the menu button, hit the equation solver button. You want the polynomial mode, you want it to be in quartic mode, and you also need to then substitute in all your coefficients on your z's. Its x's here, but it doesn't really matter. Make sure you've got the I button on the top there, going into the menu, into the setup modes, should give you complex solutions. And we get 3 minus 3, 6 plus 2i, 6 minus 2i. So there we are, we've done that question correctly. So thanks very much for watching this video here. We've now completed the chapter. Go ahead and answer lots of questions from exercise 1F. They're pretty challenging. Make sure you persevere through those difficult ones. And go on to the mixed exercise before we are tested on this at the end of the topic. So yeah, thanks very much for watching and have a go at some more questions.